I first of all want to thank the conveners and the convener organizers for putting a break between my presentation and the previous one. That I'll try and keep you guys from falling asleep, but I won't have his kind of energy. Well, I do what I can. Okay, so this presentation is the automated repair of static analysis alerts. And so this is basically a research project that I have been running for almost 2 years now, creating a tool to help you with repairing static analysis alerts. And by the way, I'm speaking of static analysis for source code, not binary. So I'm basically going to go over the problem and how we solved it. So first of all, this slide is basically about the question of is static analysis actually required to be used by the DoD. They come up with new versions of the various documentation like the STIG. And they basically say you should be using static analysis. And every time they come up with new versions, they get a little stronger. They don't require it, but they encourage it, and they encourage it a bit more strongly every time. So static analysis. I mean, how many people here have used static analysis? I see, 2, 3 hands, 4, 5, many more. Yeah, so you all know static analysis is, it finds things. That's one of the problems with it. The other problem is it has false positives. It says, buffer overflow on line 50, and you look there, and there's no buffer overflow. But the other problem is it says buffer overflow on line 60, and you look, and there is a buffer overflow. Ultimately, static analysis tools have 2 problems with them, the false positives and the true positives. So fundamentally, the goal in our project is to try and mitigate some of the static analysis tool alerts by repairing the code without worrying over whether the alert is a true positive or not. There are some alerts that, if they're false positives, just go ahead and repair the code and don't worry about trying to figure out if it's a true positive or not. So that's the approach we've taken, and the approach, well, there are probably several things we can do automatically to fix these, and I'll go over a couple of examples. We started off by repairing 3 types of problems. Null dereferences is one of them. I'll note earlier that dereferencing a null pointer was what gave us CrowdStrike, gave us the CrowdStrike problem. So this is one of the things that that we can repair. Maybe we should have them use our tool. By the way, the initial name of this project was Redemption of False Positives, because we are no longer ignoring false positives, we're actually repairing them along with the true positives. And they maybe gave a more descriptive title, but the tool itself is called Redemption. So here's a bit more analysis into the problem, which I call a deluge, that static analysis alerts produce far too many true positives and far too many false positives for anyone's comfort. So I actually came up, as Joe mentioned, I audited 25 code bases, and I came up with a bunch of, some statistics about how big the code base is, how many alerts we look at, and I came up with a similar metric of several person years to audit and repair every alert that was given to me for the average code base. However, I recently talked with Asia Cohen of C5ISR, and she also manages a lot of code auditing and has similar statistics. So I'm giving you her statistics. In particular, they've discovered that the average C code is 2 to 3 million lines of code, and they produce on average about 50,000 alerts. And it will take, and what she then says is once they run the tools, they say, well, we can audit these for you, and it will take 3 analysts 33 weeks of effort. For the right money, we will audit those for you, and most clients take a look at those numbers and they back away slowly. So ultimately, this is a fundamental problem. 3 analysts times 33 weeks is 100 weeks of effort. That's 2 years. How many people who use static analysis audit every single alert? I'm seeing no hands. Wait, do you? Okay. So for this project, we have a handful of collaborators, and one collaborator gave us his experience, which is that they get similar numbers to this. In particular, he has a list of 30 critical CVEs. Any alert that falls under those CVEs, and that includes null pointers, any alert falls under those, they audit those and they ignore the rest. So effectively, they're dealing with le deluge the same way everyone else is by ignoring the biggest part of it. You can ignore le deluge, but that means that you don't get any of the benefits of using static analysis. So again, he's filtering out all alerts except for those in the 30 big critical CVEs. He's fixing those. He fixes about 90% of the true positives, and he says about 20% of the alerts are true positives. I'm just wondering if is anyone having trouble hearing me? Hands? No. Great. Okay. All right. I won't worry about that. One other thing he suggested is that my initial notion was this would be like it. So the redemption tool is, I think of it like a spell checker. I mean, we all had trouble, we've all worked with, say, Microsoft Word spell checking the document where you just bounce from misspelling to misspelling. So to me, you could use this tool like that. The tool can just bounce from alert to alert and say, I can repair this alert. Would you like me to repair it, yes or no? And if you know, you just go to the next one. But our collaborator suggested that we should actually be putting this inside a CI pipeline. So he thought that CI pipeline would be more useful than the GUI. I think he's actually changed his mind about that, in that the GUI's become more and more important to him, simply because he wants to establish trust in the tool. He wants to see what will our redemption tool actually do to your code. One of the important things is that it shouldn't break your code, and you should trust that the repair it makes is good. Okay, so this slide is simply about what the current state of the art is with code repair, and it's very unequal. In particular, Java, the Java world gained the blessings of having the Eclipse IDE released in 2001, and it included a whole bunch of sophisticated refactoring options for Java code. So if you have Java code, it gets fixed. Well, it gets fixed automatically, or rather, every problem you see, Eclipse can highlight the problem and offer you, a quick fix. And it's pretty easy to write extra quick fixes of your own. So Java's had this kind of code repair for decades. Eclipse has an IDE mode called CDT for C and C++ development. It doesn't have refactoring. Visual Studio Code has C and C++, of course. They have some refactoring for it, but they don't repair the kinds of IDEs we have. Now, there's various research endeavors to both detect and repair code, but right now they're still in the research phases. So I'll also give a shout out to Dr. Kleber, his automated code repair project from, 2016, 2017? Yeah, the first project actually sought to repair all memory safety issues in a program by converting every single pointer into a fat pointer. And a fat pointer is simply a pointer that knows the start and end of the range of memory it can run along. So if you ever try incrementing the pointer beyond the end, the fat pointer will indicate an error. As I recall, it worked pretty well, but it does require making big changes to the entire code base. So it's a 100% solution. If it doesn't, if it screws up on any one of the problems, then your code doesn't compile, and that's bad. So, one other thing, I don't think this is on the slide. One other point is that Clang as a version 15 has had a feature where it can generate an abstract syntax tree and deserialize it into JSON. Before that, if you wanted to do work involving a compiler, you would have to use the compiler's own API. Clang's API is pretty nice, but it's still very complicated. Lots of classes, lots of methods. It's representing their the entire syntax tree for C and for C++. But since it serializes out into JSON, then I can use any tool I want to that can read JSON and slurp it up and then work with the JSON that way. So we built our redemption tool using Python, which I'm guessing it's simply we got a lot farther than we would have been able to get if we were still working with C++. It's a prototype tool, so that should be perfectly fine. But that means that now is the time to seriously look into doing repairs automatically for C and C++ code. So the solution is, I'm sure you've had a lot of people already talk to you about artificial intelligence, quantum computing, lots of fancy things. We're not doing any of that. We're doing very simple fixes, such as replacing a potential overflow integer addition overflow with, code here that will detect an error, detect an overflow, and prevent it before it happens. In this case, so this is the kind of repairs we're talking about. Simple sound engineering repairs. Nothing fancy, no AI, no quantum computing. Simple and hopefully trustworthy. So our principles are, first of all, you don't break the code. Secondly, we don't do our own static analysis. People have been writing static analysis tools since the 80s. How many people use lint? Anybody? One. Okay, well, it was a nice tool back in the day. Things have gotten a little better, but only a little. But the argument is that other people do static analysis, and we will simply take their output and apply them for certain categories. Any tool that says, integer overflow here, we can repair that. Secondly, the repair does not break the code, but it does repair the alert even if the alert is a false positive. In this case, we don't know if A plus B can overflow. It depends on how this function is called, and that depends on the entire rest of the program. But that's okay. We can fix it and prevent the overflow anyway, no matter what. So, as I said, there's two ways of using the code. The first way is simply the same way you would use a spell checker. A single developer works with a tool, with an IDE and a static analysis tool, and we're just simply adding that instead of the developer working with static analysis tool alerts and having to sift through a deluge of thousands of alerts, they simply throw those alerts at the repair tool. The repair tool goes through some plugin that we would have to write and simply lets the IDE say, buffer overflow on line 50. Would you like to repair this or not? Just like it does for Java. Actually, I'm not sure. Buffer overflows are kind of hard to do, but you get the idea. The other option is integrate this into a CI pipeline. Again, I'm assuming that you already have a classic CI pipeline set up where, in addition to the IDE you've got a version control system like Git or Subversion. CVS, anyone? Anyway, this is all controlled by a CI system, like Jenkins. And you're already building and running static analysis, and in the past, the user, again, dealt with static analysis alerts, which would come to him every time he commits something to the pipeline. But now, he no longer has to worry about that. The static analysis alerts are filtered through our repair tool, and our repair tool simply makes the repairs in a separate commit and submits a pull request. You can deal with the pull request through Bitbucket or GitHub or GitLab, whatever you want. There's already interfaces for looking at the changes that a pull request suggests. If the pull request just simply suggests repairs, such as the integer repair I just showed you, then it's a simple matter for the user to say, I accept this whole thing, merge it in, or I reject it. Now, since this pull request is automatically generated, you can't just say go back to the programmers, the original developer, saying, well, I'll accept it if you make this and this change because it's completely automatic. So it's not AI, but it is automated. So it's a matter of you can accept or it's up to the developer to decide if they accept or reject the request on their own. All right. I hope I haven't lost anybody yet. Okay. So as I said, one of the important things is that this not break the code. In fact, there's actually a dichotomy, a difference between what I want and what the collaborators want. I want the redemption tool to repair everything. It can't repair everything, but I've actually said if it can repair 80% of these alerts, then I'm good. And that was kind of a line in the sand that I drew, saying this is what we're going to try and get to. We want to repair 80% of alerts. If we don't get to that, let's try and do more. But if we get to 8%, we could possibly stop. But then our collaborator said, you know what? If you repair just 10% of these alerts and the repairs are good, I'm happy. You don't have to get to 80%. That's less important to me than just that it repairs something. I'll come to that more, but again, this is something different. This is something between what I want for the tool and what collaborators find useful, or at least minimally useful. Okay, so the point, of course, is that we want to test the tool, and so we've done a bit of testing and mechanisms. So first of all, the theory is that the things that we're repairing are effectively cert rules. As Joe said, I helped write a lot of the cert rules, so I'm very familiar with them. I'm more familiar with them than with CWEs. We will support CWEs. That is part of our requirements. That's what the collaborators want. But, sorry, I think in terms of cert rules. So the easy thing about cert rules is that these are written for the C language, and they usually warn you against undefined behavior. For instance, dereferencing a null pointer means undefined behavior. Does anyone know what the C standard says that happens if your program has undefined behavior? What can the platform do? Anyone? I think you are all correct. If the program encounters undefined behavior, then there are no longer any constraints imposed by the standard. The standard says if your program has defined behavior, it must do this, this, and this. If your program has undefined behavior, then it can do anything. It can play the game of life. It can summon the dreaded nasal demons. It can continue as if there was no undefined behavior. Or it might say, this undefined behavior I'm going to treat this as a can't happen condition. There's actually been a lot of debate recently over what undefined behavior allows platforms to do. But the point is, undefined behavior is bad, avoid it. Because that's usually where your security problems happen. Not all of them, but most of them. That's where all memory safety related problems happen. So the point is that for the redemption tool, for fixing these alerts, we are simply replacing undefined behavior with an error, with some sort of error indicator. For example, instead of dereferencing a null pointer, we simply detect if a pointer is null, and then if it's null, if we decide, oh, it is null, then we have some sort of error handling. We could just simply abort, print an error message, or if you're inside a function that already does some sort of error handling, such as returning null, then we return null. So the model here is simply that we are not changing the behavior of the code unless the behavior was undefined. If the behavior was defined, then we are adding a simple harmless check. Is this pointer null? No? Okay, carry on. Or will these integers overflow if we add them? No? All right, carry on. That's the theory why these repairs should be trustworthy. Now, I will add, of course, that this does mean a theory of, this does mean if your program depends on undefined behavior, we can't help you. We won't repair. Of course, now that does not mean that if your program, if say you're on a platform where memory location 0 actually has some useful data and you dereference your null pointer because you know that what's going to happen there, it's kind of outside our scope. If you're on a platform where dereferencing a null pointer is well-defined behavior, then no, you probably don't want our tool. Is anyone on such a platform like that? I didn't think so. I see no hands. The other thing, of course, is that if you add null checks, it makes the program just a tiny bit slower. So if the performance, it's less of an issue on performance. We will test the program and make sure that it runs just as fast as, or almost as fast as before. This does affect performance. If your program depends on timing or has timing issues so that thread A must complete in 5 seconds, or else you have a race condition, then that could also be a problem as well. But I'm assuming that if performance and timing issues are not a problem, and your program doesn't depend on undefined behavior, then you need our tool. So the way we've done the testing so far is we have 2 open source code bases, the source code for Git and the source code for Zeek. Zeek was actually requested by our collaborator. It's a language for doing network. It's useful. So for these 2, we have 3 cert rules, the null pointer rule, and the rule against reading uninitialized memory, and the rule against code that's never executed. You can remove code that's never executed and make the program a little smaller. And then we have 3 open source static analysis tools, CPP check, Klein tidy, and cert rows checkers. So two code bases times 3 rules times 2 tools times 3 tools is 2 times 3 times 3 is 18. 18 combinations. Now, all right, this is basically our whole testing mechanism. I'm not going to go through all this, but the point is we're going to go through all this to make sure that at least for those 18 combinations, the redemption tool does what we want. It repairs, ideally it repairs 100% of alerts that can be repaired. It breaks none of the code. It does detect some false positives, but that's kind of a secondary thing. You know, collaborators want to know if an alert is a false positive so that they can, and they want to be guaranteed it's a false positive. We don't want to say something, this is a false positive, and you know, it's bad if we say this is a false positive when it's really a true positive. It's bad if we repair something and repair it wrongly. It's not bad if we don't repair it for some other reason. You know, if say code is buried inside a macro, we can't repair that. We're kind of going for the low-hanging fruit and leaving the hard items to repair unrepaired. You know, leaving your code unrepaired is you know, it's no worse than it was before. The one bit of testing here that's important is this lower one, the sample alert experiments. In this case, we basically have those 18 permutations, and for each one, we want to make sure that all the alerts work. However, there's 15,000 alerts for all those, for just the tools and the rules and the code bases. So that's the deluge again hitting us. So instead of trying to repair all 15,000 or looking at them, we basically just picked 5 alerts from each bucket and made sure that of those 5, at least 4 of them are repaired. Or either repaired or recognized as false positives. The argument being that instead of having to look at all 5 alerts, you only have to look at 1 or 0. You know, ideally 0, 1 is good enough. So this is the important part. This is the useful part of our lecture. What did we learn from doing this work? First of all, collaborators have challenging data. Our collaborators prefer using CVEs, and they've often simply have that line 50 violate CVE 398. CVE 398, well, there are plenty of specific CVEs, like CVE 476 is the one saying don't dereference null pointers. If you tell me there's a null pointer dereference on line 50, I can fix it manually. If you tell me there's a violation of CVE 398, that just simply means there's a code quality problem. That's all it is. It's a category CVE. There's about 10 subcategories of CVE 398, but many tools simply say if they find a category, if they find a code quality problem, they don't know what it is, or they can't find a better CVE for it, they'll just put it under CVE 398. I don't know how to fix a code quality problem on line 350. Maybe I'll get lucky and it'll be obvious to me, but maybe it won't. So this is one problem, and this is one reason why we've been focusing primarily on cert rules, because they're more designed for security problems in C. CVEs are, of course, language independent, and they're category CVEs like that, which are harder for us to understand. Okay, so here's an example of one of the problems that we have. As I said, we're trying to solve uninitialized variable problems. So suppose you have this code that declares this variable PMBP of this type. What do we initialize it with? Right. First one is for integers, the second one is for floating points, the third is for pointers, the fourth is for structs, and the fifth is for arrays. What type is this? So the answer is, the main thing I want to point out is that while there is a right answer, the problem is if you get the answer wrong, you break code. So we have to get the type right. But, well, when we first did this, when we first ran this, we got the type wrong because we just assumed it was, since we didn't know the type, we assumed it was a struct. This actually is valid C++ for initializing many things today, but since C11 and C++11, you need to get the type right. So initially we got it wrong, we since fixed it, but doing this correctly requires a type database. By the way, this type actually is standard in Windows. It's one of the types as part of Windows. It stands for P message box parameter A. So, as I said, we're using Clang, and Clang deserializes or serializes its AST, its abstract syntax tree, into JSON. Unfortunately, right now, the JSON it gives us does not give us a lot of type information. It gives us some good type information if you simply use a type def, but if you declare a function with some fancy typing like this, you just get a string, like it's a void star or void paren star close paren, and it's up to you to parse it yourself. The good news is that we've actually modified Clang just a little bit to give us the type information in the JSON, and our plan is to mail this back as a patch to Clang so that eventually, everyone else will get this the benefit. So this is our attempt to help the open source community and make Clang just a little bit better. So this is effectively the results of our sample alert testing. For EXP34, for null pointers, we tried to repair 80%. We repaired 100%. Life is good. For uninitialized variables, we tried to repair 80%. We repaired 100%. Life is good. For code that's never executed, we tried to repair 80%. We failed. Actually, it's not so much that we failed. We decided that was not actually a good idea. So this is a cert rule MSC 12-C. It's a recommendation, and it's different from these other two in that it's always possible to make good code that doesn't dereference a null variable, and code that doesn't dereference is always better, more secure than one that does. That's pretty much agreed upon. The same is true for uninitialized variables. It's always code that doesn't read an uninitialized variable is better than code that does. But code that's never executed, you could remove it from the code, but oftentimes you don't want to. For example, Git has this line of code in about 16 cases inside the Git source code. And the argument is that argc is written here, but it's never read subsequently. However, when my developers said that had the option to remove the argc equals, they balked and they simply said, I want argc in there. Argc is being used as to indicate the number of arguments left in argv. It should not be removed. Please leave it in. Likewise, there was a file in Zeek. There was a file in Zeek which was produced automatically by, I think, Bison. And Bison, of course, produces code to parse text, and it uses a deterministic finite automata. So it has a bunch of goto labels, and any goto label that isn't actually used, it isn't the object of a goto statement, the goto labels would also register as code that's unused, and we could remove those. I don't want to remove goto labels in a DFA, so that's another case of code that we could repair, but we probably shouldn't. And that's why we have not reached 80% success rate for MSC 12. Again, we probably could do it technically, we shouldn't. That's our current feeling. All right. As I said, also there's been a dichotomy between what I want in making a high-quality tool and what our collaborators who are out there actually trying to make production-level code want. For them, the important thing is the ability to use the tool from the command line. When we first built it, it had about 10 command line arguments, and it was really hard to use. I had a hard time using it. So I think we've gotten better. Maybe we're good enough now. I don't know yet. Second thing he wants is it should be trustworthy, meaning, first of all, again, it doesn't break code, but it's also very clear about what repairs it makes. It always repairs a null pointer with a null check, for instance. So that's a matter of documentation. It's also a matter of, it would also be useful, that's the reason he's more interested in the GUI. It's more interesting and worthwhile for him to actually see the repair that the code would make, to preview it without necessarily accepting it. So that would increase his willingness to use the program to repair code automatically. If you have, say, 1,000 null pointer alerts, you don't want to inspect every one of them. What you probably want to do is inspect, say, 10 of them at random, and if the tool does the right thing for 10 things, then maybe you'll let it go on. And finally, it should repair something. Obviously, if it does nothing, that's useless, but he doesn't need 80%. He suggested 10% of alerts that it could repair would be good enough. So a couple of the goals they added is, some of our clients want to be able to use the code within a SCIF. That's fine. It doesn't actually access the network at all. They also want to be able to repair legacy code. So right now, the redemption tool runs inside a container. The container uses a modern variant of Linux. I believe it's Ubuntu 24. But people have code that runs on CentOS, CentOS 6. People have code that runs on Windows 10. People have code that runs on XP. They want to know if they can repair that code too. So this is a problem we're going to be worrying about. Fortunately, at this point, we have demos to showcase various things, and these demos are encoded in README files in the source code. In fact, here's the end result of one of the demos where we are repairing the code in red. We're replacing the code in red with the code in green. Yeah, I know this is kind of small, but this shows basically our tool at work. So, while I could give you one of these demos right now, you can always just download the code, see the README files, and step through the demo yourself. So that's what we have. The code itself is open source. We're interested in more collaborators, more people playing with it, looking at it. The code is available on GitHub right there. And there's a whole bunch of more things we want to do. Doing repairs of 3 categories is good. Doing repairs of 10 categories would be better. Doing 17 would be even better. And we would love to do that work. We'd love to support more CERT rules. We'd love to support CVEs, MISRA rules, whatever. We can also add support for more static analysis tools. And we can work on the ability to repair legacy code. Okay, and that's pretty much it. Here's the tool. I will also, one last note I will point out is that we can also use other techniques. I didn't use any AI in here. We might be able to use AI to help to work with the repair, and I'll simply give a shout out to Dr. Kleber and Dr. Flynn, who are here today, and who will be talking about using LMs to do static analysis tool adjudication. That's tomorrow at, I think, 1 o'clock, right, Will? All right, so that's the presentation.